Hi, my name is Shivendra Agarwal and I'm a PhD student at the University of Colorado Boulder, and I'll be presenting our work on autonomously guiding people with visual impairment to socially appropriate seats in novel environments, co-authored with Mary West and my advisor Brad Hayes. Being able to interpret and act on social norms is a critical part of our everyday experience with the world. One important example of this that sighted people often take for granted is the ability to find a place to sit. Imagine how difficult this task might be if you didn't have the ability to see. In this table from Wang et al., you can see a list of common mobility tasks and how blind people rated them both in terms of importance and how well a white can addresses these tasks. As you can see, finding empty chairs in a crowded public area was the highest rated task in terms of importance, as well as the lowest in terms of existing solution utility. And it turns out this is a very difficult and nuanced problem to solve. It's not enough to just identify a seat's location. We also have to be able to identify whether it's appropriate or not for us to sit there. Prior work by Stat and Groot showed that people prefer to seat themselves in a way that optimizes for privacy and intimacy. For example, if you look at this photo taken in the CU Boulder engineering lobby, you can see that people like to take seats closer to the wall, which we'll refer to as anchored seats. These seats are more private than unanchored seats. For example, they would not prefer a seat in the middle of the lobby corridor. We can also see that these students optimized for reduced intimacy, as they chose seats away from strangers. This optimization process also helps them avoid seats that may be taken. Common navigation aids like white canes and guide dogs have some limitations in finding seats. For example, canes cannot find empty seats in any targeted capacity. And while guide dogs can be trained to locate empty seats in some cases, they are cost prohibitive and don't scale particularly well. Of course, we aren't the first to investigate navigation assistance, but finding socially preferred seating is an open challenge. A good solution to this challenge must be able to map and localize within the environment, identify people and things, reason socially over all of this to find an appropriate seat, and finally, convey navigational guidance to the user. Our main contribution is a novel social reasoning algorithm for seat selection and a system that successfully integrates and operationalizes all of these components. The hardware system is primarily composed of real-sense cameras and vibrational motors mounted on a cane with a backpack-worn laptop to run perception and navigation algorithms. The software system starts with perception. We map the environment, localize ourselves, and identify people and things in the environment using onboard SLAM and mask RCNN. Identified seats are then rated with our novel goal scoring mechanism. We then use RRT star to find a path to the best scoring option if it's appropriate to do so. Auditory feedback is used to provide a plan overview, while vibrotactile feedback is used to provide online navigational guidance. Once we have the objects on the map, we are interested in assigning higher scores to seats that are more private. Our key insight is to overcount contiguous obstacles, which are similar enough to walls and can be used to quantify a notion of privacy. We consider a fixed number of rays coming out radially from each chair. Here, the rays that are in collision are shown in green. We use a sliding window that considers the rays within it and increase the score if the majority of the rays are in collision. We repeat this over the set of rays. If only a minority of rays are in collision, then the anchor score is not increased. This filters out smaller objects. A chair's proximity score is affected by its relative position with respect to other socially meaningful objects, humans, and the user. We increase the proximity score if the goal is close to the user. We also increase it if the goal is closer to objects of similar class. We decrease the score if there are nearby objects that are associated with a higher chance of the seat being not available. For example, a backpack. And we decrease the score if there are other humans close to the goal to lower the intimacy with strangers. After scoring the available seats, the best is chosen as a planning goal. The RT star trees are shown in white. The solution path is shown in orange. The live user orientation is shown in magenta. and the smoothest part is shown in blue. Finally, the plan is conveyed using two modalities. In the audio modality, we generate a semantic description of the goal's relative location with the following template. In the vibrotactile modality, bearing error is encoded into two distinct haptic animation patterns on each motor, left and right, creating 5 possible codes for conveyance. We conducted a pilot study to test the components of our system. Room 1 is a baseline single chair scenario. Room 2 and 3 are designed for locating the more socially preferred seat based on proximity and anchoring respectively. In this video, we can see a scenario with 2 chairs in the room, along with a bunch of obstacles. These users are novices who have never used a cane to navigate, but as you can see, this novice user is not able to locate a chair without guidance. With our system, the user is able to find the more private chair close to the walls, rather than the one in the middle of the room. In another run, the system notices another human, and this time it leads the user to the chair with a lower intimacy score. The pilot was successful in validating the system with novice users. We saw a 100% success rate at finding any seat, and an 83.3% success rate at finding the socially preferred seat. Even though the room had obstacles and walls, the users often were able to completely avoid collisions. The users also reported positive user experience. We look forward to expanding on our platform and these capabilities together with the visually impaired community. If you are interested in being part of this effort, please don't hesitate to reach out. Thank you.